1, welcome to topic 4.9, oxidation reduction or redox reactions. By the end of this, you should be able to balance a redox reaction equation using half reactions. Okay, so, too far. Interpreting types of redox reactions. A redox reaction is the transfer of electrons from one element to another. Oxidation cannot occur without reduction. One substance must gain the electrons lost by another. All chemical reactions except double replacement, thus precipitation reactions and neutralization reactions, are redox reactions. The substance that undergoes oxidation is called the reducing agent because it's responsible for reducing the other element, while the substance that undergoes reduction is called the oxidation or oxidizing agent because it oxidizes the one that's being reduced. These aren't directly tested on the AP exam, but it is important to note them in case you're looking at additional review materials or tutorial aids. Okay, so as some review, oxidation occurs when an atom undergoes an increase in oxidation number, and this is caused by losing electrons. We said that was Leo. Loss of electrons is oxidation. Another mnemonic to remember that is oil rig, because oxidation reduction reactions are slippery. And then for reduction, we said Leo says gain of electrons is reduction, but you could also say rig because reduction is happens when a decrease in oxidation number occurs by gaining electrons, where reduction is gain. So oxidation is loss, reduction is gain, or Leo says Either one works, whichever one works with your brain is the one that'll help you the most. Okay, so here are some more detailed oxidation numbers and assigning oxidation numbers. Reference these as you go. We already covered them in an earlier section, so I'm not going to beat it over the head anymore, and I'm going to keep moving forward. Here are some example redox reactions. Notice double replacement reactions are not here, and that includes precipitation and neutralization reactions because there is no change in oxidation state. We are also going to look at the redox method for balancing reactions using half reaction method. And they are here. I'm going to go over them though in more detail when we go through the practice. Okay, so the rules are here. We have some examples here. So review these as you go. This one would be for acidic medium because we have acids. And this one is for basic medium because we end up needing to cancel out any acid that we add by adding hydroxide. At some point they add the hydroxide here. I actually do it earlier in the steps so that way we don't accidentally carry it further. So we will go over this when we go through some examples. I'm going to pick one of these examples to do with you. Okay. So first we're going to look at assigning oxidation numbers to all of the atoms in the following formulas. So carbon dioxide. Following our rules, we have carbon and we have oxygen. Oxygen being more electronegative gets its charge of -2. That means carbon is going to balance that out and be a +4. So that way we have 2 -2s and 1 +4, which should add to the overall charge on carbon dioxide of 0. Looking at our next one, we have sulfur and fluorine. Fluorine being more electronegative is -1. So we have 6 -1 charges plus 1 unknown, and that has to add to 0. If we were to solve for sulfur, we would see that that has to be positive 6. So that way these both cancel out in their oxidation numbers. Now looking at nitrate, we have nitrogen and we have oxygen. Once again, oxygen gets -2, and we can use some algebra to find nitrogens. So we have 3 and -2 charges plus nitrogen's oxidation state has to equal the overall charge on the polyatomic ion of -1. Solving for n, you should see that n is equal to a positive 5. And so those are our oxidation states, or oxidation numbers for these atoms in these compounds. Looking at our we do, you are going to identify the elements that are oxidized and reduced in the following reaction. You should start by first assigning oxidation numbers and then looking at how they are changing. So please pause the video and do that now. Okay, so when you assign the oxidation numbers, aluminum on the reactant side and iodine on the reactant side being in their elemental states both should be 0. Then when they form an ionic compound, we would give them their charges, where aluminum would be positive 3 and iodine would be -1, so that way they add to be 0 still. Okay, looking at aluminum, we see that it goes from 0 to positive 3. That is a loss of electrons, so that is oxidation. Looking at iodine, we see that it goes from 0 to -1. That is a gain of electrons, so it is reduction, or it is being reduced. Okay. Continuing, we are going to look at number 4, and we are going to balance the following redox reaction using the half reaction method. Okay, the half reaction method works the same for an acidic solution. You just leave the hydrogen ion in there. When you have basic solution, after you add the hydrogen ions and have done all your water and everything, you have to get rid of the hydroxide ion, the hydrogen ion, by adding hydroxide ions in equal quantity. That is discussed here. Okay, so when you get to question 6, make sure you reference back to that. We will also do additional practice in class. This is just to get you started. So we're going to first identify our half reactions. Find the common species in both of these, and those end up being your half reactions. So first we have AS2O3, and it is going to change into H3ASO4. And then our other half reaction is going to be the nitrate ion changing into dinitrogen trioxide. Okay, quite obviously these are not balanced, so we are now responsible for balancing them. If you look at your rules, we have written the half reactions. Now you need to balance for the atoms, leaving hydrogen and oxygen last. So for arsenic here, we need to write a 2 next to this one, so that way arsenic is balanced on both sides of the reaction. I'm going to balance one half reaction first, and then I will repeat the process for the other one. So we have balanced arsenic. There are no other species besides hydrogen and oxygen, so I'm going to continue forward. You balance oxygen next. So first we balance each individual species. Next, we balance oxygens by adding water. So I see I have 3 oxygen on the reactant side and 8 on the product side. That means that I need 5 more oxygen, which means I need 5 more waters. So first you balance atoms, not hydrogen and oxygen. Then you balance oxygen by adding water. Finally, you balance hydrogens by adding hydrogen ions. So I see I have 6 hydrogen ions here and 10 on the other side. So that means that I need to add 4 more hydrogen ions. So that way I have 10 hydrogen ions on both sides of the reaction. Looking at both of these, I see, okay, all of my atoms are balanced, but my charge is not. After I balance all of the atoms, you then must balance charge by adding electrons to the more positive side to make them both equal. I see my overall charge on the reactant side is 0, and on the product side it is 4. So I'm going to add enough electrons to get me to 0, which would be 4 electrons. And that would then bring this to 0. So I have set this one up to be ready to add to the other half reaction and make a full redox reaction. I can't do that yet until I balance the other one though. So we're going to repeat the same process. First, balance atoms. So we balance atoms. So, and not hydrogen and oxygen. So I have 2 nitrogen. I need 2 nitrogen here. Everything else is balanced besides hydrogen and oxygen. Next, we balance oxygen with water. So I have 3 oxygen here and 6 on the other side. So that means I need to add 3 waters to the right side of my reaction. So that way I have 6 oxygen on both sides. Next step, and I'm going to run out of room, so we'll just write it down here. Next step is to balance hydrogen with hydrogen ions. So I see I have 6 hydrogens here. That means on the other side of the reaction, I am going to add 6 hydrogen ions. So that way there's 6 on both sides. Finally, the fourth step is to balance charge with electrons. So I see I have an overall charge of 0 on my product side, and on the reactant side, I see I have 2 plus negative 2 plus positive 6 is a positive 4. That means that I need to bring my reactant side charge down to 0, and I do that by adding 4 electrons. Okay. So my next step is to check to see if my electrons are equal but on opposite sides of the reaction. So I'm going to check my electrons. If they are not equal, I'm going to multiply both reactions by a coefficient, all of the species in both half reactions, by a specific coefficient. It could be 2, it could be 7, whatever it is. But to make those electrons equal. So if I instead had a 3 and a 2 here, I would multiply this whole thing by 3 and this whole thing by 2. So that way the total number of electrons would be equal and they would cancel. That is the goal, is to cancel electrons. But they are already equal, so they will cancel. So I check electrons, make sure that they cancel. Then I'm going to add my half reactions. Okay, so I'm going to move my other one over. Okay, so I move it over and I'm going to add these together. Now, if they exist exactly the same on both sides of the reaction, I can cancel or simplify them. So I see that the electrons are on both sides and they cancel out. I see I have hydrogen here, hydrogen ion here. This one cancels out and this one becomes 2. And that's kind of hard to see. Okay. I keep checking and I see that I have water here and water here. This one will cancel out fully and this one is reduced to 2. So I have simplified my reaction, and once you add everything, you can check again. But I've simplified, so now I'm going to add. So these are all on my reactant side, and these are all on my product side, so I'm going to combine them. I'm going to have 2 hydrogen ions plus 2 nitrate ions, and because it's additive rules, it doesn't matter which order they go, just as long as they are on the right side or correct side of the reaction arrow. So I have all my reactants, And I'm going to write down all my products that are left. N2O3 plus 2H3ASO4. And I check nothing is the same on both sides. So I've simplified it sufficiently. The charges cancel out. So I have an overall charge of 0 here, and then 2 negatives and 2 positives. When I add those together, those are equal to 0. So they're 0 on both sides of the reaction. And I can check 4 plus 2 plus 4 is 6 hydrogen, 2 arsenic, 2 arsenic, 2 nitrogens, and then 6, 7, 8, 9, 10, 11 oxygen, 1, 2, 3, plus 8 is 11 oxygen. So everything is balanced here. So this is an acidic solution. If I were to do basic solution at this step, I would then add 4 hydroxides to both sides. Oops. And this would give me 4 waters. So then it's now basic instead of acidic. But this was under acidic conditions as it shows us here, and we don't have to do that. But in question 6 you do. So pay attention while you work and check your answers as you go. Thank you guys for tuning in.